Live. Okay. Hello. Well, I hope everybody's seeing me now. My name is Vinicius Placco. People here call me Vinny. I'm a faculty member here at the University of Notre Dame at the Department of Physics. And my mission today is to talk to you a little bit about galactic archaeology and the chemical evolution and the age of the universe determined by old stars. So I hope you're all excited about this. Well, I'm excited, so I hope you'll enjoy this presentation, okay? So we're going to push the presentation here, so hopefully you'll be able to see my slides. Okay. Almost there. Getting there. Full screen mode. Oh, good. Okay. All set? Okay. So what I wanted to talk about is just this stellar or galactic archaeology and how do we determine the age and the chemistry of the universe by analyzing old stars or stars in our universe. And what I usually try to do in my talks is to give an alternate title for the talk so people get more excited about this. So the second title I have for you today is Cool Stuff About the Universe You Didn't Know Until This Morning. So hopefully by the end of this class, you have more information than what you have when we begin this class. So that should be good, okay? Well, first of all, well, I know you can hear me, but I cannot hear you. But I'm assuming all of you guys have Twitter accounts, right? And hopefully you're all be nodding your heads now and just trying to tweet something while I'm doing this. So I'm assuming you have Twitter accounts. So do you actually know how many tweets were sent in 2014? Can you guys just think for 5 seconds before I put the answer on the screen? Well, it's a lot, but I just wanted to try to figure out what the number is, okay? So the actual number is 200 billion tweets in 2014, okay? So you may think that's a big number, a small number, I don't know, but I want to compare this with the number of stars we have in the universe, okay? So given that we had 200 billion tweets in 2014, that's roughly 30 tweets for each living person on Earth, just as a rough approximation. So given that, do you have any idea of how many stars are there in the observable universe? Do you think it's more than tweets, less than tweets or something? And I'll just let you think about for 5 seconds, discuss that, maybe tweet something or share something with your colleagues. Do you think this number is larger or smaller than the number of tweets? So let's put the number of tweets again. And now we're revealing the number of stars in the universe. That's much larger, right? I cannot hear you, but I was expecting it right now or something like that, okay? So it's a lot of stars, right? It's just a lot of stars. And so you guys have an idea, this is roughly 10,000 stars for each grain of sand on Earth. That's pretty powerful. So there's lots and lots of stars. And the sun, which is the closest star to us, is just one of these, many, many, many stars. And what we are trying to do in our group here as astrophysicists, we are trying to study one star and actually determine the chemical composition of this star, and with that, determine the age of the entire universe. So do you think that's possible? True or false? That we can place limits on the age of the universe by analyzing a single star out of those 7 with lots of zeros in it? So, well, just a clue for you, if the answer was false, I wouldn't be here giving your talk today. Okay, so it means we can, right? If we're really clever on choosing our target, then we should be able to determine how the chemical history of the universe came to be and how the age of, and what's the age of the universe by just looking at one star. And when you look at a few of stars like this, you would think that they are all alike, they were all the same, just because, well, the color doesn't help much. But what happens is they have different colors, they have different luminosities, masses, and they evolve in different time scales. So we need to be really clever on choosing one of those stars to study. And what we do, I'm just zooming in a little bit here, and our target for today is this guy over here, right? And it has a name, a catalog name, it has a it has coordinates, and then we are trying to determine its chemical composition and then get some constraints on the age of the universe. And that's pretty powerful. And before we do that, I just wanted to show you how the matter is distributed in the universe. So we think that the universe has a lot of objects, lots of stars, and it's really big, but we don't know really much about what the universe is made of. So if we had everything on the universe today, if we could put in the screen over here, we would see that 68.3% is just dark energy. And as the name suggests, we don't know much about it because it's dark, right? So 70% of the universe is just dark energy, and we don't know much about it. 26.8% is dark matter. We know a little bit more about dark matter, but still dark, and we still don't know much about it. So it could get a little bit frustrating. 4% is just hydrogen and helium. These are really light elements. I think you know about the periodic table. So hydrogen and helium are 4% of the content of the universe. And the 0.9% here on your right, this is what's left. And then if we can split out what's left, 0.6% here are just stars, 0.35% is just neutrinos, or particles we are trying to understand now, high energy particles. And the tiny, 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 tiny yellow square here on your top right is just heavy elements. Well, that's everything we know here on Earth, right? Because, well, carbon, iron, silicon, nitrogen, oxygen, everything else. So everything we're made of, most of what we're made of, is just 0.05% of the entire universe. I think that puts some perspective on what we think of ourselves and we think about our place in the universe, okay? So the chemical elements. So talking about, well, we saw here that hydrogen and helium, 4%, and everything else about 0.9%. So when we look at the periodic table, I'm sure you are rolling your eyes now when you look at the periodic table. Yeah, I didn't like that either when I was in high school. But once you start understanding things and you start to see how this was assembled, it starts to get really, really interesting. So this is the usual periodic table, all the elements, heavy elements, noble gases, metals, and everything you were supposed to know by now, okay? And we have the periodic table in pictures. That's, more fun than the other one. And you can actually see some cool things here, like your egg yolks. They have a lot of sulfur. Arsenic is poison, so don't play with arsenic, please. Gold, you have your jewelry. So all sorts of cool stuff. So this is you can search online for that, and that's really nice. So you can actually see that strontium is one thing that you make fireworks with. So all the beautiful colors come from different chemical elements. So after that, we had another one. That's not really fun, but that's the periodic table of the nuclear physicists. Okay, so this is the nuclear chart. So you have protons and neutrons and all distribute here. The black small square are stable elements, and everything else is just things that they are observed in the lab, or they're just theories that predict that those elements would be there. And if we zoom in one of those small charts, we can see some names we know about. Xenon, barium, lanthanum, cerium, praseodymium, neodymium. And I'm not reading. I know those by memory just because, well, I have to, right? So this is one of the things that the nuclear physicists and the astrophysicists, they deal with this on a daily basis to try to figure out what's in there in the atmosphere of stars, for example. And this is the periodic table of astronomers. Okay, so there's a lot of hydrogen. So this is by mass. So you can imagine that most things we see on the universe is hydrogen, then helium, then here we have carbon, nitrogen, and oxygen, and well, neon and magnesium, some metals, and then iron. So this is more or less by mass. So we see that most of what we know and what we have is just hydrogen and helium. So why do we study stars, and especially those Metalcore stars? I will comment a little bit about. They're called Metalcore stars because, well, they have not a lot of metals in their atmosphere. So they're interesting because we think that they were born from gas clouds that were not really enriched in metals. That may seem like a little bit a weird statement for you guys, but I can show you some pictures later and hopefully this will make a little bit of sense. So the sun, as you know, is a star and it's really close to us. That's why it's so really well studied, right? It's the brightest star we can see here because it's really close. And that's why we don't see any stars during the day, because the sun is so close and it's shining so bright on us that we cannot see anything else. So here, each of those black filled dots here are actually measurements of those elements in the surface of the sun. Okay, so what this means? It means that if we look at the sun, if we try to decode the light, I'm going to show you how we do that a little bit later, we can actually know and tell you that all of these elements are in the atmosphere of the sun. Everything. So almost all of them that are found in the periodic table are in the atmosphere of the sun. And the Earth was formed from the sun, okay? So that's why we are able to measure all of those in the sun. So each and every one of those elements we can measure in the atmosphere of the sun. And then when we do that, we can actually test our theories on our theories in physics, in astronomy, and then try to extrapolate that for other stars. And other stars are usually really far, far away. So we use the sun as our proxy here, okay? So, and I wanted to just do a parenthesis here and show really quick how do stars evolve. I think maybe this is not really intuitive, but the star, if it's really massive or if it's heavier than the sun, it will evolve faster, right? Because if it's heavier, it has more mass, and then the pressure and the gravity will act strongly in this star, and then it will evolve faster. If we have really big stars weighing maybe 10 times the weight of our sun, then they will explode as a supernova here. This is the middle of our chart here. And the sun, well, luckily for us, the sun is a really boring star because it will evolve really slowly, and I think that's why the Earth was formed in the first place. So it will evolve really slowly, like this third star here, and then it will be like a red giant, and then by this time we'll already be gone, but well, that's another story. And then we have this beautiful planetary nebula, which we won't be able to see, and eventually the sun will evolve and die. So this is how stars evolve, more or less. And what happens here, when those really high mass stars evolve, they explode as supernova. And when they do explode, they will form all the elements in the periodic table in their interior. And when they explode, they will just throw these elements out in the interstellar medium. So you can imagine something exploding and just throwing all these elements in space. And what happens is the next generation of stars will be born from the gas cloud, which was enriched by that supernova. So everything the supernova formed, it would be used as a seed for the next generation. So that's why the sun has all those elements, because the sun is a product of many, many, many stellar generations. They were born, they evolved, they exploded, they enriched the space with chemical elements, and then the sun was born from that mixture. And that's why we are here, and that's why we were able to evolve as we are today. Here is a picture, well, this is a scheme of a really high mass star and what the interior is like. So you see, you have this layers here. It seems like an onion, right? So you have all these elements being formed inside the star. And when you have the iron core here, the star cannot form anything else in its interior, and that's when it collapses and it explodes as a supernova, and then you see all those colorful explosions with all the elements being formed. So all those elements here and the other ones that will be formed, they're just thrown out in space, and then the next star will be formed. Okay, so given that, this is a pretty simple picture about the universe evolving and how the metals came to be and how the chemical elements were formed and how the chemical composition of the sun and the Earth are the way they are today. So we had the Big Bang, which we believe was the very first event that gave birth to the entire universe. And right after that, as you can imagine, everything in the universe was really hot and dense. So what we did, well, I didn't do anything because I wasn't born at that time, right? So what the universe did, it formed stars, really massive stars, like 100 times the weight of the sun. So since these stars were really massive, they evolved really fast. And they exploded as supernova. Here, this red stars here. And when they evolved, they exploded, and they just threw all these elements here on the interstellar medium, is what we call the empty space between stars. And then the population 2 stars, such as the sun, were formed based, well, using all of those elements as seeds. So what happens is, we, at the telescope here today, we observe those second generation stars. So what we do is, when we measure the chemical composition of the population 2 stars, we are actually tracking the population 3. So that's why we call this stellar archaeology, because we are using one star and we are assuming that everything in the atmosphere of this star came from a previous star. And then we can know about the origin and evolution of the previous star. And that's how we're doing this archaeology thing. So where do we find these objects? And that's a hard endeavor, I can say, because I showed you the number of stars in the universe. So how can you pick good stars, right? That's kind of a challenge. And when we look at the, well, this is the Milky Way. It's a very nice picture. If you look in here, you have the Magellanic Clouds. I think, well, this is the southern hemisphere. So if you look here in the US, you would see a slightly different sky and different stars. But when you see this in sky, on sky, well, especially when you are in a really isolated area, not a lot of light pollution, well, here in South Bend, it's just impossible. But if you go outside to a playing field, no lights, you can actually see this. And this is the disk, the plane of the Milky Way, which is the galaxy we live in. And we think that the galaxy looks like this one. And we are just here where my mouse is. I hope you can see it says sun here. So here is where we live. So the galaxy is really big, and we cannot actually go outside the galaxy to take a picture because it's too far away. So what we do, we're just measuring things in all directions we can here, and we can actually try to make a map of the galaxy. I think a good analogy for you guys is that if I just gave you a piece of paper and a pencil and told you, go to the highest building in your city and try to draw a map of the entire city just by staying there, okay? So I think that's a good analogy, because that's exactly what astronomers do. We are just bound here on Earth, and the only information we get from stars is light. And what we have to do is to be clever enough to look in all directions and try to come up with this map, okay? So when people say we have a picture of the Milky Way, that's not really true, okay? So this is how we think the Milky Way looks like, okay? And this is another, well, nice picture of the Milky Way. That's not really scientific, but it explains a lot of what we want to do. So the Milky Way has this bulge with this, it's like a sphere here in the center. And we have the disk, and within the disk, you have those spiral arms, the beautiful spiral arms that you see on the pictures. And then we have what is called the Galactic Halo. This is a really spheroidal thing where all the old stars live. And what we do here to do this stellar archaeology, we just go after those old stars. We have many catalogs, and we can try to look at the colors of stars and determine which ones are older and which ones are not. It's actually trickier than that, but that's pretty much what we do. And then we go after those halo stars, those stars that are really on the outskirts of our galaxy, and those are the ones we call low metallicity, and these are the ones we use for chemical composition and the age of the universe. So the first tool we use is the telescope, okay? So I'm going to show some nice pictures of telescopes, right? Because I'm an astronomer, so I like those things, right? So these two telescopes, this here is the Gemini telescope, and this is the Canada-France-Hawaii telescope. They're both in Hawaii, on the top of a volcano, 15,000 feet above ground. As you can see here, the telescopes are above most of the clouds. And that's useful because, well, clouds usually, they are not really, well, good when you're doing astronomy, okay? So it's very good that these telescopes are this high. And actually, last year, I was working at this telescope here, and there was a really nice experience working in Hawaii on the top of a volcano with this nice telescopes. So what we do, we just have those telescopes, and then we point out to the stars, and then we do our observations, okay? We have many telescopes spread throughout the world. most of them, at least the best sites for astronomical observations, are high mountains and dry places. So Hawaii is one of them, even though it's in the middle of the ocean. It's a really high and dry place, so that's why we use Hawaii. And the other one is in Chile. Chile has the lots of mountains, the Andes, and then these are really nice places to do astronomical observations. Well, the only thing is that, well, as you can see here, the sky is really clear. So I took that picture the first day I arrived at this telescope a few years ago. And I was really excited because at that night I was going to observe, I was going to see my stars. And all of a sudden, this happened. And well, this is me, and this is, well, as you can see, a lot of snow and clouds, right? And that's not very good for astronomy. So what happens is the telescopes, they just close. And then you cannot observe, so I lost a few nights, and well, I could at least play on the snow, right? But you cannot observe when you have, high humidity and clouds and everything else. Okay, so you have your telescope, and then you need your stellar spectrum. So I'm just going to briefly explain to you what a spectrum is. And what it is, well, we have mathematical equations, right, and physics here. Well, hopefully you're not rolling your eyes right now because of the size of the equation, but just be aware that this is a simple function that gives you the energy distribution as a function of temperature. So it's just a function. So if I give you a temperature here, all of these other weird letters here, these are all constants we can calculate. So if I give you a temperature, you put the temperature here, and then you're able to tell me what's the energy distribution of a particular star that we consider this black body radiation. And when you do a plot of this, a graph, you see that different temperatures will give you different shapes of this curve, okay? And this is just as an example, this is our sun. The temperature of the surface of the sun is 5,700 Kelvin. So these are the shapes of the curves we see, okay? And what do we do with that? Then we have what we call the spectrum, okay? So this is more or less the scheme of what we do when we observe stars. We have this hot black body here that is similar to one of these for a given temperature. And then we have this cloud of cooler gas, which is represented by the atmosphere of the star. And then when you run all of this through a prism and we observe, you usually see this is what we call spectrum, and you see these lines here, right? And all these lines, they give information about the chemical composition. These are all fingerprints from the star, from the atmosphere of the star. And if you look at this one, I think this looks familiar for you guys, right? So we can actually see that here on Earth when we look at rainbows, for example. That's exact the same principle. And what is a rainbow? You have the water droplets, hanging around on the atmosphere, and then you have the sun shining its light through the atmosphere. And when the light goes through the droplets of water, this works as we actually do we have a diffraction grading when we're doing this in astronomy. And the droplets of water, they just refract the light, and then we just scatter the light in all those different colors. And this is how we see the rainbow here, which is the sunlight coming through the atmosphere. And this is the real spectra of the sun. Okay, so this is what we actually observe when we point the telescope at the sun. And as you can see, there are many, many of those dark spots here. And each and every one of those dark lines are actually a fingerprint of a specific chemical element and its different transitions. So when we use our physics theories and everything you know about physics and astronomy, we are able to decode all of those small discontinuities here and say what is the chemical composition of the sun. That's the plot I showed you before. But that's not, well, this picture here is just to show you guys how the spectra looks like. But what we actually do, we just use another type of spectra, which is this one. So instead of having all those black lines, what we have are those discontinuities here. And how do we do? So these, in this case, these are hydrogen lines. So I know that there's hydrogen on the atmosphere of the star. And what can I do to measure the abundance of hydrogen, for example? I can just measure what is inside this line here. For example, I could use a really simple geometry and just try to draw a triangle here and calculate the area of the triangle, and that will give me actually something proportional to the hydrogen abundance in that star. So this is a different spectra. This is lots of carbon, but we'll just skip that for now. And let's go to our Metalcore stars. So these are low metallicity stars, and we think those were formed really, really, really early in the history of the universe. So, well, as I showed you before, we have lots of equations, and some of those look ugly, but they are really, well, they're actually simple. We're just using a log here and doing a ratio and just doing some subtraction, right, of these quantities here, the number of atoms in the star and in the sun. So these are the classifications we have for those Metalcore stars. We have Metalcore, very, extremely, ultra, hyper, mega, and well, you can come up with your own classification if you want, right? So, and that's one thing we do just to make things easier for us when we are observing targets, okay? And this is how a spectra of a Metalcore star looks like. So we saw the spectra of the sun, right? And this is a really narrow part of the spectra of the sun. And as we go to lower and lower metallicities, you can see that the lines get smaller and smaller, and that means they have less metals in the atmosphere of those stars, okay? So these are the stars we go after when we want to determine chemical composition and ages. So to determine the chemical composition, what we usually need is the spectrum. We need a physical model of what's happening on the atmosphere of the star in terms of temperature, gravity, how the matter is just behaving in the atmosphere of the star, and we need our atomic nihilists from the nuclear physicists. We need a lot of information for them. And that's what we call the nuclear astrophysics. So we're just blending the astrophysics with the nuclear physics, and we're working together to determine the chemical composition of stars. So we need both of them, because the nuclear physicists will provide us really accurate information about how the chemical elements behave, and then we can go to the star, well, we can look at the star and measure that. And this is a really weird plot of a carbon and nitrogen abundance determination in a star. So each and every dot was actually measured on the atmosphere of the star, and the black line is our best model for the atmosphere of the star. So this is for a nitrogen determination and for carbon. So as you can see, even though sometimes we miss a little bit, we do a pretty good job in determining the abundances using these methods. Okay, so if we compare the observed with the model, that's actually not bad. And we can actually tell, how much carbon and how much nitrogen we have on the atmosphere of the star. And then which of those elements would be useful to determine ages? So I'm sure, well, I'm not sure, but maybe you heard about this half-life concept. It's just if you have a sample of a given element here, if you wait a certain half-life, after that half-life has passed, you would have half of the weight of your element after that period of time. And this is the equation that drives that behavior. So if you think about carbon, maybe you heard about carbon-14. So that's used for archaeological sites to determine, well, chemical dating of old samples in archaeological sites and all of that. And the half-life of the carbon-14 is 5,700 years. Okay, so what that means is if I have 1 pound of carbon-14 in my hand now, well, I would probably die, but assuming that I wouldn't die, I would have it here in my hand, and 5,700 years later, if I was still alive, I would have half of that mass. Okay, I would have half a pound. So that's what we use. But if you want to determine the age of stars in the universe, that's not very useful, right? Because 5,700 years is not a lot. So we have other elements we can use to determine ages. And as you can see, the half-lives here are really, really different, right? We go from carbon, that's 5,700. We go to rubidium-87, that's 48 billion years. And then we have cadmium and tellurium. And I don't even know how to speak that age here, okay? So when you look at this table, which element do you think would be best to determine the age of the universe, for example? And I can give you a clue. The age of the universe is 13 billion, well, it's almost 14 billion years. So what we would do, we would not use this one, right? Because then it would require a lot of half-lives, and then your sample size would be really small. And this one, nothing would happen, right, in the age of the universe. So what we do, we usually use uranium-238, and we use thorium-232 to determine the age of the universe. based on what we measure in stars. So what we do, we go to the atmosphere of the star again. This is that spectra again for different stars. And we can try to measure here. Can you see this tiny blip here that I'm pointing with the mouse? You can see that there are 3 red lines, and this is our uranium determination. So the points are the observed star, right? And here's the uranium line again. That's really a challenge. So that's why we have huge error bars. But well, we try to do the best we can. So when we measure those abundances in the atmosphere of the star, so how do we go from abundance to age? We have other relations, other equations to determine the age. Well, it's a calibration, I would say. But if you measure the abundances of thorium and uranium in your star, you can actually measure iridium, osmium, europium, and all of those weird elements as well. And then you do ratios, and you do the log. You multiply by a constant that is given by theories and experiments, and you can actually determine, or you can place limits on the age of the universe. Because if you think about it, no star can be older than the universe, right? Because the universe came first, the universe was formed, and then we started forming stars. So when we determine the ages based on these measurements, this is what we get. Well, this looks like a weird plot, but it's actually simple. So this is one star. It was studied first in 2001 and then 2009. So what the astronomers did, they measured those ratios. They went to the spectrum, measured europium, uranium, and other elements. They used those equations here, and then they actually estimated the age. So these are the ages they determined, the black dots and the blue squares. And this here, this constant line, here's the age of the universe determined by the Planck satellite. So it's a totally different concept, different math, physics involved, and they have a pretty small error bar. So we're pretty sure that the universe is actually this age here. So as I told you, no one can be older than the universe. So what happens is, as you can see, our star, this is the same star. So since we have lots of uncertainties when we measure the abundances, it's hard to, for these values to be all the same. But as you can see, if we compare with the line here, we're actually doing a pretty good job. And even though we're not able to determine an exact age of the universe, we can actually place limits, right? If I look at this star here, assuming I didn't know about the line, okay? What I could say is that, well, if my star is 14 billion years old, well, maybe the universe is at least 14 billion years old, okay? It couldn't be 12 or 10, because then the star would have born before the universe, and that's not possible. So this is one thing we do to determine those ages. And again, as I told you at the beginning, this is just one star out of that 10 to the 22nd, 10 to the power of the 22nd stars we have in the universe. There's a lot more than tweets. And just by looking at one star, we can actually place constraints to the age of the universe. And as boring as it looks like, this is the star from which we determine the ages here in this plot. As you can see, it's a really boring star. As you can look, it's just gray here. But as you can see, it holds really important information if you were, smart enough to look at the star and interpret the light, and using all the theories that the physicists are working on for hundreds of years, and the astronomers as well. So if we collect everything and we observe the star and the sky with different eyes, then we are able to do a lot of interesting things, okay? So the takeaway, I think, from this presentation that I want you guys to be aware of is that we're here bound to Earth, okay? We have lots of stars outside, and the only information we can get from the stars is light. And what we do is we have to use our ingenuity to interpret the light and have more information about where we came from. And the last picture I wanted to show you to end this talk is this nice picture, again, from telescopes on the top of a volcano in Hawaii. And can you see the lasers here? These are actually lasers. And what happens is the telescopes, they emit lasers throughout the atmosphere to try to compensate for some turbulence. And this picture is real. It was taken, I think, 4 or 5 months ago. And these 4 telescopes here, they were pointing to the same direction, which is the black hole in the center of our galaxy. So since the night was kind of clear, they were using those lasers to point to that place. And I thought you would enjoy seeing that, and that those are real lasers, which is pretty cool. Well, thank you very much for your time. I hope you have enjoyed, and if you have any questions, I would be happy to answer them now.
It'll take a minute for him to catch up.
Should I go back to the... Should I go back to the...
While we're waiting for questions, can you say why you got interested in astronomy?
Well, to be honest, when I was a child, I wanted to be an astronaut first, and then I wanted to be a firefighter. And that was not, well, then I noticed that I couldn't go to those, professions. And then when I got into high school, I started to be interested in physics. Even though I wasn't really good at math, I liked physics. So when I went to study to get into university, I kept liking physics more and more, and then I got into physics to do my physics degree. And then within the physics, they had this astronomy program, and I was looking at all those nice disciplines and studying stars and galaxies, and well, I got interested, and some years later, I'm here. Oh, and by the way, I'm from Brazil. That's why my English sounds weird. Yep.
What is known about dark matter?
Well,
repeat the question.
So the question was, what is known about dark matter? Well, not a lot. So we know about dark matter from just how it interacts with the regular matter, the matter we can see, right? So we know that dark matter has some gravitational interaction with the rest of the matter. So that's how the astronomers and physicists detected or assumed that dark matter existed in the first place. So we cannot actually see, but we can actually infer from the interaction with the matter we can see. So that's what we know about dark matter. And we keep studying this just as a gravitational interaction with everything else we know about. Yeah, that's I think the simple answer.
What's the difference between dark matter and dark energy?
Oh, so what's the difference between dark matter and dark energy? That's tricky. I think, well, dark matter, as far as I know, is the thing there's this gravitational interaction with the visible matter we see, and the dark energy is another thing that is responsible for the acceleration of the expansion of the universe. So they have the dark name, attached to it because we don't know much about it, and we cannot detect that directly. I think that's why the dark is in there, but they have different applications and they are in different scenarios, I would say.
What part of your job do you like the most?
Giving talks to high school students. That was easy. So, well, to be honest with you guys, I like everything. I feel really lucky to have the opportunity to come to work every day and do stuff I love doing and interact with, good people, intelligent people. I get to travel, all places throughout the world. And as I told you, I'm from Brazil and I'm here in the US now. I've traveled to Japan, India, Europe, and all sorts of places. I've been in telescopes in Chile, in Hawaii. And I think that's really rewarding to find something that you really love doing and you keep persisting doing that. Well, it's a lot of study, right? You have to do your bachelor's degree, you have to do a master's, a PhD, a postdoc. You're studying your entire life. But if it's something that you really love, I have fun, well, almost all the time. So I think I love everything about my job.
What advice would you give to a high school student who wants to study astronomy?
Okay, my advice to a high school student who wants to study astronomy. Well, first of all, I think you have to know your math, your physics really well, starting from high school. Because well, even though you're going to learn a lot of additional math and physics when you're in college, when you're at the university, many things you're learning right now will be really useful as the basis of everything else you will learn in the future as an astronomer, for example, right? If you're curious about astronomy, just go to websites, read cool stuff about the Hubble Space Telescope, the new missions, and if you're really, really, really interested about astronomy, you can actually write an email to an astronomer like myself, asking questions. We can set up meetings with your high school, for example, and we can talk about things you can do going forward in your career. So I think the advice is that, and be curious about stuff in general, because astronomers, as physicists, as chemists and biologists, we are all scientists, and scientists are just curious people by nature. So be curious, and please study a lot of math and physics in high school. Go study after this talk, please.
Will the universe expand forever?
Will the universe expand forever? That's a very good question. And that's a subject of a lot of discussion. There are many theories that think that the universe will just expand forever and will just, at some point will be so expanded that it will freeze out and then it will just end. People think that theories can think that the universe will just stop expanding and then will start collapsing again and go back to what it was before. So there are many, many different theories. And the good thing is that with this new missions, space missions and theories being developed now, I think some years from now, we have a more certain picture of what's really happening. And well, that's not my field of research, but that's, I think, the furthest I can go with this information. But there's lots of theories.
So we understand the importance of basic research. However, there must be some examples of practical applications that come from this research. Do you have some examples that you could share off the cuff?
Oh, that's a tricky question. Well, there are many examples in physics. For example, the GPS you have on your phone, that's based on Einstein's general relativity theory, which is 100 and something years old. And when it started, nobody think it would be of any application whatsoever, right? If you think about astronomy, one thing that I can say from my specific field of research is when we go to these telescopes, we have all this amazing engineering going inside the telescope, right? You have these huge cameras. They're not megapixels, they're gigapixels, right? You have cameras, you have, all this mechanic, engines that have to be in place. So all of these, to some extent, the CCD cameras, for example, they are in your phone today, so you can take pictures and do stuff. These, well, the development of those, it's to some extent driven by astronomy observations, because you want better and better cameras with better capabilities to observe fainter and fainter targets. But one thing about really basic research, like this research I do, is that sometimes we don't see the practical applications right away, but then after 50, 100 years, you would see, well, something that was driven by that. Even though maybe there's no direct application now, maybe the problem I want to measure abundances maybe with 100 times more precise than I had before. So the technology that will be developed for me, to allow me to do that, maybe would have some applications in industry and other things later.
Okay, very last question. How can you detect a black hole?
Oh, that's interesting. So how can you detect a black hole? So the black hole, as the name suggests, is black. We cannot see it. But what we see is actually what happens around the black hole, because then it's a really strong gravitational pull. So we see that the luminous matter around the black hole is moving in a very weird way. And that's how you can predict that the black hole is there. Well, oh, here's me again. So thank you very much for having me. I hope you had enjoyed this. And if you have questions, you can write me. Gina can put my email in there. You're free to write me with questions. And I hope you enjoyed, and thank you very much. And have a good day, and study math and physics, please.